All right, so this is part 3 because I was about to pause the recording, and as it turns out, there is no way to pause a recording. I think it has to do with streaming, it cannot be paused. Anyway, so let's continue, right? So um, the discussion goes like, okay, now we are actually back in the notes. So the question is, how do we perform this summation in a closed form if it is possible? So we have a sigma notation simply representing this. I is the expression, basically expressing each term that we are adding. And then this loop here, which is I going from 0 to x inclusively, is specifying, how many iterations or the iterations that we need to perform and the value of I for each iteration. So this by itself is not going to be helpful because it's just really the same as this, except it looks nicer. So what we did next was to figure out that there are two cases. One is when x is odd, and the other one is when x is even. When x is odd, the number of items that we want to add is even because we start from 0. When x is even, then the number of items that we need to add is odd because we start with 0. So there's an item in the middle of the entire sequence that does not work out, that doesn't have anyone to pair up with. So I'm not going to go through all the explanations again. However, I can briefly explain. So from the first to the second, I'm just breaking up into whether x is odd or not. This is when x is odd, and this is when x is even. When x is odd, there is an even number of items, so we can pair up the first with the last, the second with the second last, and use up all the items. And when x is even, then we have an odd number of items. So we can do kind of the same trick, except the one in the middle is on its own. It is not part of either of the sigmas. So if you look at the sigmas, this is the first half of the items. This is the second half of the items. So what we did, the next step is probably the trickiest of all the steps, is to combine the two sigmas into one, but sharing the same indexes. So that is the trick, because we want to share the same indexes. The index still goes from 0 to x minus 1, the whole thing divided by 2. So the trick to do this is to observe that when I equals to 0, it covers the last item of the second sigma, from the previous line. And when it gets to the last item, when I equals to x minus 1, the whole thing divided by 2, it's going to cover for the first item of the original sigma of the line before. Now, I know this one has a plus 1, and this one does not seem to have a plus 1. But that's going to work out, because if you subtract this amount, if you subtract this amount, x minus 1, the whole thing divided by 2, from x, it will get you back to this particular number here. And I do the same trick over here. You can see how the two sigmas are combined into one, but I did not change the index range of the first sigma in the previous line. And I do the same trick over here. Instead of summing over the expression of I'm now summing over the expression of x minus I. And once we perform this step, we can see that x is the only thing remaining because I minus I cancels out. I minus I also cancels out, so we only get x left over here. But x does not depend on I, which means, if I say, oh, let's just add x to x to x to x while I is going from 0 to 1 to 2 and so on, I'm really just multiplying. So the number of times that I need to multiply x with is x minus 1 divided by 2, which is the last index value. And then we have a plus 1 here because the index starts from 0. Same trick over here. This index starts from 0. It ends with x divided by 2, the whole thing minus 1. So the minus 1 is gone because we have to add 1 to the count. So it becomes just x divided by 2. So now we have these two expressions. And then just using algebra, it goes all the way to the last form, which basically is telling us that regardless of whether x is even or not, we still get the same expression, which is nice. So x times x plus 1 divided by 2 is going to get us the natural number that we need to assign to the coordinate of x0. In other words, any pixel on row 0 is going to be, we can work out the natural number for those pixels using this final form, which is pretty easy to compute. So the next thing that we talked about was how do we get back to the value of the other pixels? In other words, now that we know how to figure out the natural number for all of these particular pixels, what about this one over here? What about this one over here? What about this one over here? That becomes the next question. So during the class, I basically presented this picture over here and ask about, okay, what about the natural number that is supposed to assign to the pixel of row 9, column 18, which is this little pixel over here. So I also gave you an observation of what is the next pixel on the same diagonal line. So that turns out to be 19.8 because if we go in this direction, we have to add 1 to the x part of the coordinate and subtract 1 from the y part of the coordinate. And then if we do that again, we get 27, then the next one is 21.6, and so on. So one observation is, if you add the x and the y coordinate of the pixel, and all the pixels along the same diagonal line is going to have the same sum when you add the x and the y coordinate, because you can see how 18 plus 9 is the same as 19 plus 8, which is also the same as 20 plus 7, which is also going to be the same as 21 plus 6, and so on. So that means it's pretty easy to figure out the coordinate of the pixel at the base of the diagonal line on row 0. So in this case, it is 18 plus 9, which is 27. So we know the coordinate of the pixel at the base of the diagonal line is going to be 27, 0, which matches the form that we were working on earlier, because in other words, if we go back to the notes, it is in this particular form. So in this case, x is 27. So now we can have 27 times 27 plus 1, which is 28, but the whole thing divided by 2. That will give us the natural number corresponding to this particular pixel here. So given that we know the natural number of this particular pixel, the next question is how do we go back to figure out the natural number of this particular pixel here? The next pixel, which is this pixel here, is going to have the coordinate of 26, 1, but in terms of the natural number assigned to it, it's going to be the natural number of this pixel just plus 1, because that's how we scan the diagonal line in order to assign the natural numbers. So that gave us the idea of, oh, okay, so if we know the natural number of the base of a diagonal line, all we need to do is to add the y value of a particular pixel on the same diagonal line to figure out the natural number of that other pixel. So this particular pixel is going to have the same, is the value or the natural number corresponding to 18.9 is going to be the natural number of 27.0 plus 9, because this is the only difference that we need to add to the natural number of 27.0. So we generalize the equation so that the general equation for the natural number corresponding to xy is going to be x plus y times x plus y plus 1, the whole thing divided by 2 plus y. So that's great, because now we have a way to quickly and easily compute the natural number of any particular pixel. And from that part on, the discussion continues to talk about, okay, let me see the notes here. So we're done with this part here. And all of this is really the same as what we talked about, except it's all written out. So from there, we want to know, whether this is, what is the inverse function? Because earlier I already said this is inductive and also surjective. It is a bijection, and any bijection has an inverse function. So that's what we're going to talk about on Wednesday, which is tomorrow, because we want to know the closed form of the other way around as well. So that should conclude the makeup of